Greetings, welcome to Project Dig's recap number 4. Project Dig is a 2D multiplayer automation survival sandbox game that I am developing here entirely on Twitch and uploading all the VODs to YouTube, along with these recap videos. It's been a while since we did a recap. I'm going to recap about half of what we've done since the previous recap video, and then I will make another recap video soon that touches on that second half and a little bit more. So yeah, we have been busy. We're going to cover some audio, animations, and netcode in this recap video and show off a little bit of what that looks like. And go over all of it. So first up, audio. We use FMOD for the audio. FMOD is a library that, let me just pull it up here, that allows you to have like reactive audio. So it actually, you can have game inputs going to the audio that then affect it. So you can have like sound effects that change based off of the time of day. And so it's a pretty cool library. We're using that. We got the very basics of it down and show you what that looks like. So we have an audio namespace here, and we just can initialize it, set up our banks, and then you can play events and that's pretty much it. It's really basic right now because we don't really know exactly how we want to use it. So we only spent like a day working on this. But we actually did get it functional. I believe I can show, I think I have my audio turned off here. Let me turn that on. Desktop audio. Yes. So that is coming from the game, and that's going through this FMOD. So we actually have it loading up as a resource, and it loads up this bank that we can then play sound effects from, and we can also adjust the volume for the sound effects and the different buses and everything. Right now it's really simple, but we can build upon it as we kind of discover what we actually need from the audio system itself. So after we worked on that, we moved on to animations. Animations are broken up into two different parts. There's the normal sprite animations, and then there are spine animations. We'll go over the sprite animations first. So sprite animation is like a single frame is represented in the image. We take a texture rect of that image and then display that on screen, and then after some amount of time we play the next frame. So we take another section of the texture rect, we render that. And so the animation system's all about knowing where those are, what are the frames, which is the texture rect, and I think we have it up here. Yeah, frame is a texture rect, the offset, and the duration. And then an animation is composed of multiple frames and its total duration, and then if it needs to be looping. And so for that we made an animation namespace so we can load up all of the animations in the game that have these like normal sprite animations, and then we can look them up. And what this means is that we don't have to store the animation, like all of the animation data, so you know, these frames and duration, on the individual components. Instead we store them here And then on the component itself, I have a component right here, we just index into it. We say, oh, here's the index, here's the animation index, here's the frame index. So we can look up the animation as well as the frame that we're currently playing and be able to get like the text direct and the offset, duration, etc. And then, you know, update the render components so that way it displays it correctly. Additionally, we added in an animation system, and that just, you know, updates it. It says, oh, this much time has elapsed, and, you know, if the animation has finished, then move on to the next frame, or if that frame has finished playing, move on to the next frame. And that's what all of this is doing here. So yeah, it's working pretty well. We kind of have some stuff hard coded right now with the oil slime and like how the animation file is being set up. I'm still not entirely set on having this like animation file where all the animations are stored. I might do something else. But I do like this. What this means is that we are able to keep our animation component really simple and not duplicate a lot of data that we would, you know, if we spawn 50 oil slimes and have them playing these different animations, we don't have to duplicate all of the frame information for each oil slime. They all reference into here. And that worked out pretty well. The other part of the animations, the spine animations, unfortunately, it gets a little bit more complicated. Oh, and before I move on, here are what our animations look like. We can have it play in a little tack animation. So those are our oil slimes. It works. It works. Spine animations are quite a bit more complex. The spine is kind of like FMOD, but for sprites. Kind of. Esoteric software. Here we go. It allows for very complex 2D animations that have bones and skins, and it's composed of a lot of different smaller sprites, so the sprite sheet is very slim, but it means that in order to be able to have all that functionality, there's a lot of complexity in the code, and so we had to add in support for that. Fortunately, Spine has an official C++ binding or API, so we were able to use that and pull that into our engine and then change it some. But we didn't change it too much because it's quite a bit of code. It actually ended up being, at the time we implemented it, about half of, or like it was equal to the amount of code that we had for the entire game engine. I think it was like 7,000 or 8,000 lines of code that we added. And so there's a lot of stuff going on there. I'm not going to go over all of what Spine is doing. We'll just go over how we are using it. So the two main things is the skeleton and the state. The skeleton is tracking all of the data for the like where the bones are at, and for the individual entity. And then the state is more of about like the animations that it's playing, and if it needs to be transitioning to different animations, or if there are animations queued up, etc. So our spine component ended up being kind of a a joint animation / render component because it has all of the rendering information stored inside of here as well. And so for our spine component, we had to do some things that kind of compromise our ECS system, but for now, I think it's the best solution. So we have our shader in here, that's fine. But yeah, we have these pointers, which means that this is no longer a pod, which does add quite a bit of complexity for several things. Going to see if I can come up with a better solution for this. But for now, it's working. So let's see here. I think the majority of it's in here, right? No. I'm actually kind of forgetting exactly where we put. I guess it's mostly in sorry. Animation resource, that's where it'd be. So in our resource, we had to load up the atlas, which is what tracks all of the images that contribute to the spine animation. And then we use the atlas to load up the skeletal data. And then once that's all loaded, that's when we can create our final spine resource that contains the skeletal data as well as the animation state data. And so this is like the core data that is used whenever we are creating a new instance of the skeletal data or the animation state data. Just like what we did with our simpler animation system, where we have the indices that index into this more complicated stuff. Here instead of using indexes, we used pointers for it, because that's how the system was set up. And so that's how that's all working. Hopefully I'm doing an okay job explaining this. It's been actually like 2 weeks since I worked on it, so I'm kind of already it's not super fresh. So yeah, I can show you what it looks like running. Here we go. We have our little dude here, and we have the bounds that's dynamically changing based off of that animation size. And so this guy actually has a lot of different bones on it. Eventually I'll probably add in rendering to show bone. Oh, maybe. I don't know how much we're going to be using bones. But yeah, so he actually has multiple bones moving, and his sprite is quite small. If we open up our data file, we can see that this guy is composed of this here. So that's pretty cool. Oops. It turned out well. And so yeah, just let's wrap this up. The last thing to show off for this recap video is the netcode. So network. I wanted to add in some basic support for networking and just like get that figured out. I was originally planning on using RackNet because that's what I use for Korea, but then after talking to some people, I changed my mind and ended up using Steam. I think it's actually called like Valve, or maybe Steam networking sockets or something like that. Game networking sockets, which is developed by Steam. It's based off of the Steamworks SDK implementation. It's kind of like a branch of it, or a fork. And so we ended up using that because it's very close to Steam, and that's our like primary target platform. and that will make it easy for us to like hook it up to be able to do like joining your friends easily and seeing your friends playing and whatnot. So I got the basics of that working. Actually, let me go back here. So we can set up a server, shut down, send packets, receive packets, broadcast packets, handle them, or handle, this is setting up callbacks, and then do the same with the client. And we also even have a local, so you can be able to send packets to yourself as a client to the server. So that's very convenient. So I can have the host be able to act as a client and a server, so that way I can write off the game code and kind of have the host be treated as both and not like have to have a very clear distinction of the two. So that ended up working pretty well. So we use our, actually I keep jumping. We use our write stream here to be able to send data or broadcast it. And then we have our callbacks. I think it's here, callback handler, callback. Where's our callback at? Here we are, which takes a read stream along with the world and the connection. So that way we could easily see who is sending the data and have access to the world, as well as be able to read the stream. So I have an example working here, and you've actually already seen it in action, where we make it, whenever we are creating an entity, we have this write stream. We then say, hey, this is a request entity creation packet. We specify which one it's going to be and the location, and then we have the server broadcast that. And up here, we have the client handling that request entity creation with this callback, which is defined up at the very top. And so whenever we receive this packet, we then, I guess actually I should go here where we are handling it. So this is on the client. So whenever we receive it, we pull out the message type, which would be the like entity creation request. We then call the corresponding callback if it exists, which gets to this point. And then we create that entity locally and then set up the transform, move it to the location we want. And if it contains a spine component, we tell it to play the walk animation. So that's how this is all working. So that's like about 10 days of work. I think I maybe went a little long on the explanations. There's a lot of like different things that we worked on, which made it, take a while to kind of recap. Like I said, I'll be doing another recap soon. But yeah, I just want to thank my patrons for supporting me and all of the viewers for joining and keeping me company while I work on this. If you guys have any feedback on these recap videos or on any of the VODs or anything, I would be happy to hear it. So yeah, thank you for watching, and I will see you next time.